Hey, AP Chem. We're going to continue talking about chapter 17 and different types of thermodynamic functions. Today, we're going to look a little bit more at entropy, and specifically, we're going to look into all the different types of entropy of the system, entropy of the surroundings, entropy of the universe, and the implications for all of these. So we'll start by looking at the entropy of the universe and the second law of thermodynamics. If you were curious as to what is the first law of thermodynamics, we've actually already talked about it. It's basically this equation, E equals W plus Q. Total energy can be described as work and heat together. So it's kind of like the conservation of energy. Energy can be transferred from work to heat, from heat to work, but energy is not going to be created and energy is not going to be destroyed. That would be the first law of thermodynamics. The second law of thermodynamics is on your screen. In any spontaneous process, there's always an increase in the entropy of the universe. I feel like I need some background music, like maybe the Twilight Zone when I say this one. It feels so big. In any spontaneous process, there's always an increase in entropy of the universe. So notice that it doesn't say increase of entropy of the system. It doesn't say increase in the entropy of the surroundings. It's increase in the entropy of the universe. Okay, so from this point on, it's really important that you distinguish between those three types of entropy: system, surroundings, and universe, because they imply different things and they indicate different things. And the only one that indicates spontaneity is going to be entropy of the universe. The other two are part of it, but by themselves, they can't tell you if a process is spontaneous or not. Only the entropy of the universe can do that. Again, this is like a summation of everything we talked about in the last video. Nature moves towards the most probable state available to it. So if disorder has a whole bunch of states and order has one, then nature is going to move towards disorder, towards the many probable states of disorder, not the one probable state of order. So therefore, because nature moves toward the most probable state available to it, entropy of the universe is going to be increasing when we're talking about a spontaneous process. So these three entropies can all be related in an equation. So we talked about this already. System and surroundings, if you have the system and you have the surroundings, those two things together make up the entire universe. So if you sum, the sum of entropy of the system plus entropy of the surroundings is going to equal the total entropy of the whole shebang, which we label the universe. Now, just like in chapter 6, where we kind of lived or died, hopefully more living than dying, off of signs, the same is true in this chapter. The signs of entropy are probably more important than dealing with the actual magnitude, than dealing with like real numbers inside it. And in fact, just like we saw with enthalpy, a lot of the test questions, especially multiple choice questions, are built around the signs by themselves. So sometimes they don't even give you numbers. They just give you the signs, and then they ask you to predict what's going to happen. So let's talk through the signs for entropy of the universe. If entropy of the universe is positive, that means the entropy of the universe is increasing. Okay, so your perspective in that case is going to be the universe. If it's positive, the universe is increasing. And therefore, the process is spontaneous. So if you go through all of the hoopla and you end up with some magnitude of positive entropy, you can conclude right there that the system is spontaneous. Okay, again, not entropy of the system, not entropy of the surroundings, only entropy of the universe. Okay, if entropy of the universe is negative, that means the opposite is true. The entropy of the universe is decreasing, so entropy of the universe is becoming more ordered, and the process is spontaneous in the opposite direction. Or the process, as it's stated, is not spontaneous, and therefore the reverse of the process is going to be spontaneous. And then if the entropy is 0, what does that mean? If positive is spontaneous and negative is non-spontaneous, what is 0? So 0 means there's no net change that has occurred. And we have a term for a system where no net change is occurring. Maybe there's a forward reaction. Maybe there's also a reverse reaction. They can be continuously occurring, but if they're occurring and kind of equalizing each other out, so there's no net change, we call that system, we say that system is in dynamic equilibrium. So if the entropy of the universe is 0, that means the process has no tendency to occur. It has no tendency to occur in a net reaction kind of way. Again, forward and reverse reactions can still be happening, but no net change is occurring and the system's at equilibrium. Okay. Oh, here we go. Here we get a little summation of our two laws of thermodynamics. So the first law basically says energy of the universe is conserved. Entropy of the universe is not. Entropy is increasing. Energy is just transferred. It's conserved. Okay, so a little bit more about entropy of the universe. So here is a really good practice for us to go through. Actually, I want to go through one of these together and leave a couple of these to go through as a class. So here we have our reaction we just looked at. All right. And basically they're asking you, is this going to be spontaneous or not? So for example, here, they're not telling you magnitude. They're just telling you the sign. And so if the sign of entropy of the system is positive and the sign of entropy of the surroundings is also positive, then what's the sign of entropy of the universe? Now, again, they don't give you magnitude, and so you have to consider all possible magnitudes. But if entropy of the system is positive, the entropy of the system could be 0.00001, or it could be 1, or it could be 100, or it could be a billion. No matter what it is, it's positive. If system is positive, surroundings is positive, what is the universe going to come out to be? And do the magnitudes make a difference? So pause this video, think about it, come to a conclusion, and you can come back to this video. So if both of these things are positive, entropy of the universe must come out positive as well. There's no scenario, no matter how big or small entropy of the system and entropy of the surroundings are, there's no scenario where entropy of the universe comes out negative, which means if these two are both positive, then this system has to be spontaneous. Entropy of the system is positive, entropy of the surrounding is positive, entropy of the universe is going to be positive, and therefore the system is going to be spontaneous. Okay, look at the next two. Pause your video, see if you can make a prediction on the next two, and then come back and we'll talk you through it. All right, the next scenario is really similar. So in this next scenario, you have entropy of the system is negative, entropy of the surroundings is negative. So what does entropy of the universe come out as? And is there any scenario where it doesn't come out to be that? And in this case, if both of these things are negative, no matter how big or small the numbers are, entropy of the universe is always going to come out to be negative, and therefore it's going to be non-spontaneous. No matter how big or how small entropy of the system and surroundings are, entropy of the universe is always going to be negative. Okay, now let's look at the last one. The last one is the most interesting of all the cases. So entropy of the system is positive. Entropy of the surroundings is negative. Does this come out to be spontaneous or non-spontaneous? And the answer here is, it depends. It depends. If entropy of the system is the bigger value, has the bigger magnitude, then it's going to come out positive. If delta S system is larger. Oh, here we go. We can be even more succinct. All of our kindergarten teachers would be proud. We'll use the alligators. So it's going to be positive if delta S system is greater than delta S surroundings. Okay, however, if delta S of the surroundings is greater, then it's going to come out to be negative. So if delta S of the system is less than delta S of the surroundings, then it's going to come out to be negative. So in this case, it depends. It could be yes or no, depending on the magnitude of each. So that's the real question. If these two are in opposition to one another, which one is going to come out on top? Before we can answer that question, we really need to know a little bit more about entropy of the system and entropy of the surroundings. We've talked about entropy of the universe, and we've kind of talked about how we a couple different ways on how we can define these two. But entropy of the system, your one little system that you're looking at, and entropy of everything else really need to be treated differently. So before we can answer this question, which one will dominate the other one, we really need to know a little bit more about these two. So let's go explore entropy of the system and entropy of the surroundings. Now, what you're going to find out, this whole section, is how spontaneity is dependent on temperature. So here's your key. Here's kind of our purpose for the next couple slides. Temperature is going to make the difference here, but why? Why does temperature make a difference in terms of the spontaneity of the process? And this is getting back to like exo versus endothermic. Okay, and we saw this before when we were looking in chapter 6 with enthalpy. We did see that systems that tend to be exothermic tend to move forward on their own without any intervention, but that's not always true. There are cases where endothermic processes, like the melting of ice, are spontaneous as well. And melting of ice is a really good example because, again, it's temperature dependent. If you're above 0 degrees Celsius, it's going to be spontaneous. If you're below 0 degrees Celsius, it's not spontaneous anymore. So we definitely see this dependence of spontaneity and temperature. So where does that come from? How does that factor in? And can we deal with it quantitatively? Let's take a look at that in the next couple slides coming up. All right, so to look at this idea, we're going to look at the vaporization of water. So if something is vaporizing, it's turning from a liquid into a gas. So vaporization of water. Let's look at the entropy of the system and the entropy of the surroundings for this specific case. Okay, so entropy of the system for the vaporization of water. All right, if I were to ask you from the perspective of water, looking at the water itself, if water vaporizes, what is happening to the entropy of the water itself? And if you were going to answer this, here, let me write out a little process reaction before we move forward. So H2O liquid goes to H2O gas. Okay, so if you were to answer this, what you would probably say is entropy is going to increase because of a couple different factors. So this would be a good time to pause the video and see if you can jot down a couple different factors. Why is the entropy of gaseous water higher than the entropy of liquid water? Pause it now. Okay, and you should come up with a couple different reasons. So first of all, temperature. The gaseous water is going to have absorbed more energy. It's probably going to be at a higher temperature, right? Water is liquid under 100 degrees Celsius. Water is gaseous above 100 degrees 100 degrees Celsius. Now that's true unless you're talking about water vapor. So let's just divide this into two concepts here. So you're going to have the concept one of a pot of water on the stove, okay, and below 100 degrees Celsius, water is liquid. Once you reach 100 degrees Celsius and go above it, or you pump more energy into it, that liquid water is going to absorb energy. It's going to expand. It's going to turn into a gas, and it's going to turn into gaseous water. Okay, so that's scenario one where the vaporization of water could occur. Scenario two is a cup of water sitting on the counter. And over time, right, if you leave a cup of water on the table, what's going to happen to it? Eventually, the liquid molecules are going to escape into gaseous molecules. So that would be the evaporation of water, right? And that is not dependent on temperature. That is just a phenomena that occurs. If you put water into an evacuated container or put most solutions or solvents into an evacuated container, they're going to form a vapor pressure above the liquid, right? Because the liquid molecules just spontaneously come out and establish a set amount of molecules above the liquid, and that is what we call vapor pressure. Well, if that system is not capped, then the liquid will come out and disappear, and then more liquid will come out and disappear, and more liquid will come out and disappear. So both of these cases are examples of liquid water turning into gaseous water. One of them is dependent on temperature. So if you listed temperature as a factor here, you would be correct. Temperature can definitely push this reaction forward. However, there's also this idea that we just talked about positional probability. So think about water as a liquid and how many different positions are available to that liquid. Now, there's quite a few, right? Because the molecules can be variable distance away from each other. The molecules can slide past each other. The molecules can have movement. They definitely do have movement. Okay, so there's a bunch of positions available to liquid. However, there's more positions, way more positions available to water as a gas, right? Water as a gas can have even more variable distance. Water as a gas has even more space where the molecules can spread out and occupy. So as far as positional probability goes, there's far more positions available to water as a gas than there is to water as a liquid. So this is also going to be a driving force. So we can see for the vaporization of water, a driving force forward can be temperature, which comes down to enthalpy, right? But it also can be positional probability. You have temperature as a factor in the first one, but not the second. You have positional probability as a factor in both of these. So this is the factor we really want to hone in on for entropy of the system. Entropy of the system is very dependent on positional probability. If you can predict the sign, or of the positional probability, which one has more positional probability, which one has less positional probability, then that is going to be the sign of entropy of a system. So these two things you definitely want to link together. When you think entropy of the system, you want to think positional probability. Okay, so here we kind of continue on with that thought. Notice if you have 1 mole of liquid, you have 18 milliliters. If you have 1 mole of gaseous water, you have 31 liters, or if you're at SDP, you'd have 22.4 liters, right? So which one has more positions available? Well, the gas does. It takes up more space. It's going to have more positions available. So therefore, if you move from a system with less positions available to a system with more positions available, entropy of the system is going to be positive. Okay, let's just recap because that was a lot of discussion. So for entropy of the system, the sign is going to be dependent on positional probability. And if you're moving from a system with less positions available to a system with more positions available, entropy of the system is going to be positive. So that would be solid to liquid. That would be a positive change in entropy of the system. That you could go liquid to gas. That would also be a change in entropy of the system. You can go from a solid into an aqueous form. Remember, we talked about how that's very true for polar molecules. You can't always make that statement for electrolyte solutions, which dissolve ionic compounds, right? So solid to aqueous for sure for polar things that dissolve. Sometimes for ionic things that dissolve, sometimes not. But you can definitely make that statement for polar things that dissolve. So all of these factors we talked about before, that they really link to entropy of the system. So now that we've talked about that, let's talk about entropy of the surroundings. So for the vaporization of water, entropy of the surroundings, think about that. So that's everything in the universe except for water, because water's our system. So if you take the water out, it's the beaker the water's sitting in, the counter it's sitting on, the floor the counter sitting on, the atmosphere above it, the walls of your room, the trees outside, the planet Earth, all the people, the space, the stars, the planets, the black holes. Okay, all of that is going to be described by the change in surroundings. So how could we possibly talk about the change in surroundings? Talking about the surroundings, all of that in terms of positional probability is just not practical to do. It's just too much to consider. So it's really hard to describe the positional probability of all of those things and how they change. So rather than doing that, what we look to when we're looking at entropy of the surroundings is heat flow. Heat flow, we can talk about. Heat flow, we can describe. We did it all chapter 6, right? You can tell me if heat is flowing into a system or heat is flowing out of a system, right? You can tell me if heat is flowing into the surroundings or out of the surroundings. And so in this case, this is something practical that we can describe. So entropy of surroundings is going to be directly tied to the heat flow. Now, you do have to be careful with this because this is the only time in any of our discussions on thermodynamics where you're not thinking from the perspective of the system. Here is the one and only time where you're going to be thinking from the perspective of the surroundings. And how do you remember how to do this? Well, because it's labeled, right? You have a subscript of surroundings. So for this one and only time, you need to be considering the sign from the perspective of the surroundings. So if heat is flowing into the surroundings, then entropy of the surroundings is gaining heat. That's going to be a positive. And that's what it says right here. The opposite is also true. If energy is flowing out of the surroundings into the system, entropy of the surroundings it's losing energy, entropy of the surroundings is going to be negative. So before we talk about our system, the vaporization of water, right, it might be helpful for you to contrast two things. So think about enthalpy of the surroundings versus entropy of the surroundings real fast. Okay. So in an exo versus endothermic example here. All right. If you're talking about an exothermic system, right? So entropy versus enthalpy of the surroundings. In an exothermic system, heat is flowing from the system to the surroundings, right? Heat is flowing, that's like holding something hot. Heat is flowing from the something you're holding into your hand, from your system into your surroundings, right? Okay, so the enthalpy of that is heat flowing out of your thing and into the surroundings. Enthalpy is going to be negative. Okay, entropy is going to be, if you're thinking about the thing you're holding, that's hot. Energy is flowing out of the thing into the surroundings. So your surroundings is gaining disorder. Your surroundings is gaining energy. The surroundings is gaining disorder. So entropy of the surroundings in that case is going to be positive. Okay, now would be a good time, and pause the video, really think through that same scenario for endothermic. Obviously, it's going to be opposite, but can you put that into words? Okay, so for your hot thing that you're holding, okay, now you're holding a cold thing. It's an endothermic system, right? You're holding an ice cube. So heat is flowing from your hand into the ice cube. Well, enthalpy of the surroundings, heat is flowing out of your hand into the ice cube. Enthalpy is going to be positive because heat is flowing into your system, into your ice cube, out of the surroundings. Entropy, on the other hand, your hand is the surroundings. You are losing energy to the system, the ice cube. Your hand is losing energy, losing heat, becoming more ordered. So entropy of the surroundings is negative. Okay, that's a little confusing to walk through, but it's an important distinction to make. For everything else, we always imagine from the point of the system, except for this one term, entropy of surroundings. This is the only term where we really flip that perspective and think from the point of the surroundings. Okay, so now that we have kind of established what is positive and what is negative for entropy of the surroundings, and that what we're going to consider for this is the heat flow in and out of the surroundings. Think about our system. Okay, vaporization of water. Okay, and it's probably easiest to think of in terms of this with the pot on the stove, but you can imagine either scenario. Either scenario should lead you to the same conclusion. Okay, is our system endothermic or exothermic? Well, in order for liquid water to turn into gaseous water, does energy have to be absorbed or released? Energy has to be absorbed, right? Liquid water absorbs energy, turns into gaseous water. Okay, so heat is flowing out of our surroundings into our system. And so entropy of our surroundings is going to lose that heat flow. It's going to become more ordered. And so entropy of the surroundings is going to be negative. Okay, so here we have the third scenario we talked about in the last page. Entropy of the system is positive. Entropy of surrounding is negative. So what is going to happen to entropy of the universe? Oops. Entropy of the universe is made up of entropy of the system plus entropy of the surroundings. One of those is positive, one of those is negatives. So when does the vaporization of water occur? And is it a spontaneous process? Well, it depends on the magnitude. Which one of these terms is going to be bigger? And that depends on temperature. Okay, so again, think, when is this process spontaneous? It depends on the temperature. Okay, so here's the deal. Temperature is going to have an effect on the magnitude of entropy of the surroundings. Remember, entropy of the system is more dependent on positional probability. Entropy of the surroundings is more dependent on heat flow. And the temperature makes a difference for the heat flow more than it does for the positional probability. And so the magnitude of entropy of surroundings is going to be temperature dependent. Okay, so we already talked about the sign. You must have the sign correct in order for this all to come out correctly, right? So the sign is going to indicate direction of heat flow. For an exothermic system, the sign of entropy of surroundings is positive. For an endothermic system, the sign of entropy of the surroundings is negative. Okay, so we have to establish the sign first of all. And then the second is magnitude. Now, it's kind of an interesting concept here that magnitude is temperature dependent. And that has to do with kind of the degree of change that occurs. So let's think about it in terms of heat, and then I'll give you kind of an analogy to think about it. If you are at a low temperature and heat transfers into that system, that heat is going to have a bigger effect than if your temperature is already at a high system and that same amount of heat transfers in. If you need that in words, it's down here, by the way. Again, think of like transfer of heat as a bundle of energy. And if that bundle of energy transfers into a low energy system, the degree or the percentage of change is going to be bigger than if that same bundle of energy gets input into a high temperature system. Now, it's helpful to think of the effect of temperature in terms of movement of the particles. But think of an analogy. This analogy is kind of helpful too. Think about giving $50 to a billionaire versus giving $50 to a student, right? Same bundle of energy, the same bundle of energy is going to be our $50 bill, right? If you give that $50 bill to a college student who is at a low temperature or a low financial position, right? That college student is going to flip out on you. They're going to be so excited. They're going to run, they're going to dance, they're going to hug people, they're going to kiss people, right? They're so happy you just gave them $50 because they don't have very much. And that input of money is going to make a big difference to them. The percentage of change that this makes for the college student is big. If you gave that same $50 bill to a billionaire who has so much money that they don't know what to do with it, and so they feel the need to launch rockets into space, they're going to go, thanks, right? It's not going to be as significant to them. It's not going to make a very big percentage of change in their financial life or their emotional life, right? So the same bundle has a bigger change and a low system than a high system. And it's kind of the same with energy. That same amount of energy, that same bundle of energy, if you put that into a high temperature system, it really doesn't affect the change in entropy as much. If you put it into a low temperature system, there's a bigger percentage of change that occurs. And therefore, it can affect things more. So let's kind of take a look at this. Okay, so entropy of the surroundings is dependent on the temperature, right? The temperature is going to determine whether that quantity of heat that transfers in is significant or not. So it's dependent directly on that quantity of heat that transfers in or out. It's indirectly affected by temperature. And this kind of gives you another logic flow here. So the driving force for spontaneity is provided by the energy flow, right? It's affected by the magnitude of energy because that affects the change in surroundings. And so we're going to analyze this in terms of quantity of heat divided by temperature. So heat divided by temperature, joules divided by Kelvin. All right. So again, let's look at these terms, exo versus endo. So here's our exo versus endo systems. We're thinking in terms of entropy of the surroundings. And you're going to look at the sign, the quantity of heat that's transferred divided by the temperature. Okay, so here we have that in an equation form, entropy of the surroundings. You see the sign here, and then you have enthalpy divided by temperature. So if you have the enthalpy and the temperature, you can figure out what the entropy change of the surroundings is, which is a piece of spontaneity, right? Spontaneity is determined by entropy of the universe. Okay, entropy of the surroundings is a part of the factor that makes up the entropy of the universe. So instead of looking at it in terms of change in entropy, you can consider this in terms of enthalpy over temperature. And so we've been talking all along about how temperature definitely affects things. The endo versus exothermic reaction definitely affects things, but you see here, it's only a piece of it. It's not the whole picture, right? It's a piece of what affects spontaneity, but so is positional probability. And these two things together can determine spontaneity. Okay. This here in the middle is just a quick little reminder. If you're talking about enthalpy or the heat change under constant pressure, the term in your numerator is going to be enthalpy. If you're talking about the heat transfer under constant volume and therefore variable pressure, the term in your numerator has to be energy. We have it here as delta U, but we've been talking about it so far in terms of an E. So remember, your conditions are going to change the numerator for you. Enthalpy versus total energy. Okay, so now would be a good time to pause and take a deep breath and try to write a sentence summarizing what we've just determined. Enthalpy and temperature certainly affect spontaneity, but it's not the whole picture. Positional probability also affects spontaneity, and you need to take both of these things together in order to determine whether a system is going to be spontaneous or not. Also, before we move on, I just want to point out the negative in this term. Okay, and that goes back to the other slide when we were comparing enthalpy versus entropy, right? For an exothermic reaction, enthalpy is negative, whereas entropy is positive. So that's what that negative in the equation does. It flips the sign for you, so you don't have to conceptually think through it. It mathematically flips the sign for you, so you don't have to process that conceptually. They're trying to help you out there, basically. Okay, so this is definitely an equation you should know. It's not the most common equation used on the test. We'll kind of get there to the most common equation, but it's definitely a testable equation. So you're going to want to be able to deal with it mathematically. You're going to want to be able to deal with it in terms of signs, which is probably more important to do than dealing with it mathematically. You're also going to want to be able to explain it conceptually. So if they give you half of this, can you draw your conclusion and write that conclusion and reasoning in a sentence? The whole claim evidence reasoning platform really comes into play in this chapter. They like to give you free response questions that they expect you to stake a claim, provide evidence, which is usually the equation, and then reason your way between the claim and the evidence. Again, being able to deal with signs here is really important. If you have an exothermic reaction, enthalpy for an exothermic reaction is negative. The equation throws in a positive there for you, and therefore entropy of the surroundings is going to come out positive. Okay, here's a great example. I'd really like to go through this together as a class. And then after we go through this example, we're going to get into our last thermodynamic quantity, which is free energy. Okay, so let me know what kind of questions you have, and I'll see you in class.